So our claim was that we had this function, x prime t, which we had defined as x prime e to power minus I over h, minus I over h bar ht x, and we said that this is equal to an integral over all possible paths of e to power I over h bar the action corresponding to that particular path, where action was just defined as in the classical mechanics. It's a function of integral of the Lagrangian from 0 to t, Lagrangian which is a function of x dot x and t, possibly t. Now let's, what was the Aharonov-Bohm effect? There was a magnetic field in a localized region. So we said then there is a corresponding vector potential. Also outside, the vector potential is non-zero outside, although B is equal to 0 because the vector potential has to be continuous. And so we were looking for, one thing we can look for is the transition in the interference pattern. We can put a screen over there, send our particles through, let's say, a double slit, and look at the interference pattern on the outside. Now, the interference pattern will be basically depend on this matrix element, x prime e to power minus I over h bar ht x. X is this point, let's say x0. It will depend on this thing. So here, we should consider all paths that start from x0 and at the, let's say this is the point x prime and at x prime. And the Lagrangian of our system is the Lagrangian in the absence of the magnetic field or vector potential plus, what's the Lagrangian of a particle in a vector potential?
Just potential.
No. The scalar potential is 0, phi is 0. The vector potential is non-zero. Well, it should involve A, and it will involve Q. Well, you see, we said that the Lagrangian is a scalar. So it should be a scalar. We cannot have a vector in a Lagrangian. What are we going to multiply it with? The velocity. So now the path integral e to power I over h bar s, we can divide it into two. A sum over the paths where xt goes above plus a sum over the paths where xt goes below. But you see, dt, no, not dt. Let's look at two paths, s xt minus s x prime t, where both x and x prime goes above. Now the difference will be just dt from 0 to t, let's say. It will be just this term, q v v dot a minus v prime dot a. v dt is nothing but dl by dt times dt. So this is nothing but dl. So if you go from 0 to t dt q v dot a, this is equal to q a dot dl from x0 up to x prime. Now if you go from x0 up to x prime, a dot dl over path 1 minus x0 to x prime a dot dl over path 2, this is nothing but A dot dl. But this is also equal to curl of A dot ds. So this is equal to 0 if both paths go above or below. Now both of them should be either going above the magnetic field or both of them are going through below the magnetic field. And it's equal to phi b if path 1 goes above and the other one goes below. So what we can do, now we had already split it our actions in this form. This is equal to e to power qi over h bar A dot dl above times dx e to power I over h bar is 0. Why? Because we had seen that whatever the above, whichever above path we choose, this integral will be the same. So when we are summing over all these xt's that goes above, they will all contribute this phase. They will all contain that phase. And this integral, you just evaluated it through any path that goes from x0 to x prime above the magnetic field. And you do the same thing for the other one, from x0 to x prime below the region of magnetic field of A dot dl, and dx e to power I over h bar, again s0, xt goes below. And this is nothing but qi over h bar A dot dl, let's say above, times 1 plus e to power qi over h bar, the magnetic flux. Now that's not 1, that is, let's say, m1 plus m2. So basically, the interference pattern depends on the flux there, although the electron, even if you create a region which the electron cannot enter. Well, this was basically the Aharonov-Bohm effect, and this is the Aharonov-Bohm phase. So you see, if you want to study the Aharonov-Bohm effect, this is kind of trivial. In the other case, we had to deal with all these phase transitions, gauge transformations, or the adiabatic transition, etc. But here, kind of a couple of lines. Well, at most 2 pages, let's say, describing the problem and showing that it has physical consequences. 2 pages on the screen. Now let's look at some other stuff. Now our claim was that this formalism just using this one, let's call this one our no. Well, this is basically equivalent to our Schrödinger equation. Now, let's also try to show that. But before that, I mean, in quantum mechanics, you have probably heard that the classical equations are satisfied as expectation values. Let's try to see that here. You see, this measure we had defined it as some kind of a limit. dxi. And each dxi integral went from minus infinity to plus infinity. Now, if we just make a change of variable, this is equal to instead of xi plus delta I minus infinity to infinity, the measure doesn't change. You can just let's say yi is equal to xi plus delta I, or xi is equal to, well, let me do the other way around. Xi is equal to yi plus delta I, then the integral of xi is actually equal to the integral over yi. Even the limits are the same. So this measure is actually equal to the path integral over the y's. So what does this tell me? dx e to power I over h bar s x. Now I will just make a change of variable. Instead of x, instead of x, I can just use the yi as my new variables. Y plus delta, let me just call that function delta y in the continuum limit. E to power I over h bar s x plus delta y. Now, up to this point, I didn't use anything. I just made a change of variables. Now I will be using the fact that the measure doesn't change. Now this is y. E to power I over h bar s y plus delta y. This, let me just rename everything again. dx e to power I over h bar s y plus x plus delta x. This time I just renamed my y as x. So dx e to power I over h bar s x minus e to power I over h bar s x plus delta x. This should be 0. I'm just subtracting the right-hand side from the left-hand side. Well, if delta x are small and arbitrary, that basically means that dx e to power I over h bar sx times delta s should be equal to 0. But this is basically some kind of a matrix element, let's say. Do you see how it becomes the matrix element? No? Okay, so let's do it explicitly. You see, this G, x prime t, we had defined this as x prime e to power minus I over h bar h t x. Let me just make a change of notation. We have this term. This is equal to e to power minus I over h bar h epsilon minus I over h bar h epsilon minus I over h bar h epsilon e to power minus I over h bar. Okay. So we have this term, and we can kind of identify this state as our state at t equal to 0. So this, we just write in this form. Kind of we are evolving in steps of epsilon. So this operator here, let's say it acts at the time t prime. So I will just call that Hamiltonian h of t prime. Just a label. It doesn't mean that Hamiltonian is time dependent, not at least in this picture. Hamiltonian is not time dependent, but just to put it as a label, to label that it acts at the time, it acts at my state at the time t prime. Okay? In that case, that exponent I can just write as the dt prime h of t prime from 0 to t prime. With that notation. What is this t? Well, it's the time ordering operator. This is just a change of notation, nothing else. I'm still sticking to the Schrödinger picture, where in the Schrödinger picture is the states that are time evolving. So ht prime, let's say, acts on my state at time t prime. When my state evolves until the time t prime, at that time ht prime acts on my state. But if I would have gone to, I don't know, Heisenberg picture or the interaction picture, it would be more rigorous. But for the time being, in this picture, it's just labeling. I stress that Hamiltonian is not time dependent. Okay, so with this in mind, then our G is x prime time ordered product x. Now again, xt prime, this is equal to x, but acts on my state when it evolves until the time t prime. Again, the operators are, I repeat, the operators are time independent. I'm just labeling when my operators are acting on my state. My state is evolving, and when my state, the evolution of my state comes to the time t prime, then I'm acting with this state. So I can just write this matrix element, x prime, e to power minus I over h bar h t prime, x e to power minus I over h bar h t minus t prime. I first evolve my state up to the time t prime, then x acts on my state, and then I let my state evolve. This will be equal to x prime time ordered product of x t prime e to the power minus I over h bar h dt. X. Again, I repeat, just notation. The operators are time independent. But you see, if you remember how we drive the Hamiltonian, how we drive the path integral, we just inserted identities at various times. Now, we insert an identity at the time t prime also. But when we insert an identity at the time t prime, this operator acting on that, it just gives me the xi, where I corresponds to the xt prime. Are you following? Okay. You see, how did we evaluate? Well, let's just do it explicitly. This is equal to this is the operator over here. X prime, 8 power minus I over h bar h t minus t prime. Now I insert x hat, I insert the identity x double prime, x double prime, x double prime, 8 power minus I over h bar h t prime x. This is equal to, well, I can take the dx double prime out. This is x double prime, because x hat acting on the state x double prime just gives me x double prime. And then I have x prime 8 power minus I over h bar h t minus t prime, x double prime 8 power minus I over h bar h t prime x. This is equal to dx double prime x, well, this first matrix element I can just write as a sum over the paths that start at the time t prime is equal to x double prime, and at the time t it is equal to x prime of 8 power I over h bar integral of the Lagrangian from t prime to t. The other matrix element is the sum over the paths that start at t equal to 0 at the point x, and at t equal to t prime at the point x double prime of 8 power I over h bar t from 0 to t prime L dt. But I can just, you see, what I am doing is I am summing over, I have this x initial point, I have this x prime, the final point. So there is this x double prime. I am summing over all paths that start from x and goes to x double prime. And then I am summing over all paths that start from x double prime and goes to x prime. Then I am summing over all possible values of x double prime. But that is basically I am summing over all paths that start from x to x prime, with the condition that x double prime is equal to x at t prime. So that becomes sum over all paths. This time the only restriction is at t equal to 0, it starts from x, and at t equal to t prime, it is at x prime. Now x double prime is nothing but the value of my path at the time t prime. 8 power I over h bar. Well, the exponents, they are just numbers. They are no longer operators in this path integral representation, so I can just combine them. And so I get an integral of the Lagrangian from 0 to t. That is my action. S of x. And remember where we started from, this is equal to x prime. X, I have the time evolutions, and then I have the x at t prime. So if I put an operator over here, that becomes this matrix element over there. Well, let's see. So I have this operator over there. It should be 0. That's the matrix element corresponding to that delta S, which should be 0. But this is nothing but the Euler-Lagrange equations in expectation values. So classical equations do exist in the quantum mechanical world for the expectation values of the operators. And it's quite general. I mean, this, at least in this formalism, is quite general. Let's derive the Schrödinger equation. This is the classical equation. Now, let's look at del G by del X. This is equal to the path integral of the sum over path of e to the power I over h bar s del over del x. This is equal to del x I over h bar del s over del x. Now remember, x is the final point on my path. E to the power I over h bar s. Do you remember in classical mechanics what this corresponds to? So let's see. What is this? To calculate that delta s over delta x, what we are actually doing is we have, let's say, this is our initial path, this is our final point. We are shifting, no, this is the initial point. This is the final point. We are shifting the final point slightly, so there will be a very small variation of my paths. This is delta x. Let's look at how the action changes. Delta s will be equal to the integral. It's the integral of the Lagrangian, so the change in the Lagrangian. This is equal to dt dl over dx, delta x plus dl over dx dot, delta x dot. This is equal to d by dt, delta L over delta x dot delta x times dt plus dt delta L over delta x minus d by dt dl over dx dot delta x. But we had just seen that this is nothing but the variation of the action with delta x at t equal to 0 is equal to delta x at t final equal to 0. But we had just seen that that is equal to 0. It is this one over here. In the variations, we didn't change the endpoints. We just shifted the intervals. The xi are just the points on the trajectory of my particle only in the internal. They are not the endpoints. The endpoints were fixed. And we know that that variation is 0. So we are left with the first one. And the first one, delta s is equal to dl over dx dot delta x when t goes from initial time, let's say, to the final time. But dl over dx is nothing but the momentum, dl over dx dot. So this is equal to final momentum delta x final minus initial momentum delta x initial. Now, in this derivative over here, we are differentiating with respect to the final point. Now let's just, okay, this is the final point. So the initial point is fixed. If the initial point is fixed, the variation of the initial point, this is equal to 0. So del s over del x is equal to p. So we have this expression over there, dg by dx is equal to this one. This is equal to dx I over h bar p e to the power I over h bar s. This p is the final moment. Well, we can take the second derivative, dx I over h bar p squared I over h bar s. Del s over del t. Lagrangian doesn't have any explicit time dependence, let's assume. Hmm? This is, let's see, from 0 to t, dt, okay, so d by dt, L. Hmm? Hmm? Well, this becomes minus h. Well, you see, as you are changing the time, you are also changing the endpoint. So it's the derivative with respect to time basically becomes also involves the derivative with respect to the endpoint. So that's why it becomes the, remember, L is equal to P dq minus h. So you get this one. So what do we have? dg by dt, this is equal to dx, I over h bar, ds by dt, h power I over h bar s. This is equal to dx, I over h bar h, h power I over h bar s. This is equal to dx, I over h bar. Now this here I have a minus. Let's say p squared over 2m plus v of x. Remember, all of these, by the way, are at the end points. At the end. So t is the time at the end of the evolution. X would be the position of the end point of my path, etc. And as I'm changing my paths, I'm keeping the endpoints fixed. So anything that is a derivative with respect to the endpoint, I can just take it out. Anything that depends on the position of the final point, I can just take it out because the path, all the paths, they go to the same end final point. This is equal to I over h bar minus I over h bar over I del over del x squared, because all of these derivatives bring me a factor of p, 1 over 2m, plus v of x, and I can just take all of these out. And if I take all of these out, the remaining is a sum over all paths of this phase, which is nothing but g. So g satisfies the Schrödinger equation. So although we started by showing that g should satisfy the Schrödinger equation, now the claim is if we have g, we can formulate everything in terms of g, including the Schrödinger equation. So g satisfies the Schrödinger equation, and since the time the state at any time can be written as x, or let's say g, x prime t of psi x prime at t equal to 0. Any state can be written in this form. Since g as a function of x and t satisfies the Schrödinger equation, psi satisfies the Schrödinger equation. So in this sense also they are the same thing, basically. And in the long, and if you can solve a problem using one of either the Schrödinger formalism or the path integral formalism, You can solve a problem with one of them, then you can solve the problem with the other one. It's just with one formalism, certain things will be easier than the other ones. And it turns out that the path integral formalism is much easier to solve numerically. Path integrals. Because we don't have to take the limit as epsilon goes to 0. We can just assume epsilon to be very small but finite. And we can assume the space is also finite. So we have a finite number of integrals which can be evaluated numerically.
These x's are general, right? If you can write a Lagrangian out of it, you can choose that they don't have to be coordinate position. That integral doesn't have to be between 2 points, but two different states.
You mean these x's? Well, for example, in field theory, now we will not be studying field theory, but in field theory, basically these are fields. Fields are just functions that are defined at every point in time. So you can just generalize this straightforward manner. So this x is just some quantity that you describe your problem with, some function, let's say, that changes as a function of time from at t equal to 0 up to some time t. And then what you do is you just have to identify an action corresponding to whatever the parameters that you are using to describe your system. You have to define an action. And then sum over all possible intermediate paths that connect your initial configuration to the final configuration. So in that sense, x doesn't even have to be the coordinate, as you said. And if you can write the Lagrangian, you can do the quantum mechanics.
So if their x's are phi, so the wave function depends on fields.
If?
Wave function depends on fields. If the x are phi, yeah, positions are fields.
Okay. Then psi.
Wave function depends on fields.
Sure. You see, for example, one thing that you can do is constraints. I mean, in quantum mechanics, how you do constraints? You write a potential. For example, if you want to confine a particle in a box, what you do is outside the potential is 0, inside the potential is non-zero. What if the constraint cannot be written in such a form? You see, the only thing you have to do is just restrict your summations in these paths to the path that satisfy your constraints. You don't have to worry about anything else. So, for example, constraint system, quantization of constraint systems turn out to be much easier with path integrals.
Without any calculation, say this is.
Yeah, that is imposing the constraint. I repeat, I'm not saying that the path integral is superior or weaker, but it just has its superior points and its weaker points.
Okay, so if we take our constraint as has to go from a single point. I mean, it starts from here, it could end from any of these points, but it has to reach this point. So we get the diffraction.
Let's see. You mean this one, the double slit or single slit?
Which is easier. But it's not easy.
Well, you see, diffraction is kind of trivial. You are already summing over actions. And if you're already summing over paths, so you can imagine one path going through here, another path, or you have these paths. So you already get the interference pattern. So it's just the differences in the phases that causes the interference.
So what if there is a single slit? What's the difference between like starting from a point and going to points, or like starting from instead this the point where diffraction is? Right?
You see, for example, one thing we can say, do you agree that the dominant contribution will be from the classical path?
Yeah.
Okay. So the dominant okay, so the path integral, we can just divide it into two. Again, the paths that start from here and go to cross this region, and the ones that cross the lower region. So we can divide the path integral into g lower plus g higher. No, not yeah, plus. And then g lower, we can divide it as, let's say, this is x0, this is x1, this is a, this is b. G lower, we can just divide it into two. From x0 to a, then from a to x1. And from the higher, no, this is the higher one, b plus x0 to b, then from b, no, a to x1. So this is still path integral. And then the problem is, what is this b x or ax? In those regions, it's a free particle, kind of. So you can just use the free particle. Or you can just say, okay, so I'm just considering the classical path. This is the classical path from x0 to a. This is the classical path from x0 to b. And then I can consider these classical paths. And action for a classical action for a free particle. Remember, this is dt 1 over 2 m x dot squared, which is equal to 1 over 2 m v squared times t. This is equal to 1 over 2 m x final minus x initial squared over t. Well, if you remember, this was the exponent in our free particle path integral. So then you see these different paths, this plus this, this plus this, will have different phase factors. And the phase difference will be nothing but h power I over h bar delta L. The differences in the length. Well, kind of related, let's say. Because basically the path integral depends on this length difference. Well, it will not be just delta L, but it will depend on this length difference. So we get the interference pattern.
But you do it like for just one x1, then for other x1s, and then you find the pattern.
Well, you see, what you mean by the pattern is just, you just look at x1. And then as you change x1, you see that the amplitude just increases, decreases, increases, decreases. So you get this interference pattern. Or if you use light, let's say this is 1 over 2 m delta x times v. For light, it is easy because v is just c for light. So in that case, it just becomes delta L, the differences in the length, if you just use light rays. Well, for particles, it will be particles with a mass. Basically, you get the interference pattern. It will be modified, but basically the idea will be the same. Okay, let's give a break, and then we will go back to the harmonic oscillator. Hmm?